dumbass.
Right? So
No, I at
density,
least trying to
you
understand.
use per,
I know.
right?
It's like
1 kilogram is 1,000 grams. 12.01 grams of carbon is 1 mole of carbon, right? 1 mole of carbon has 6.8 grams of atoms, right?
Okay,
Atom, 1 mole.
so let's chit chat. So let's start with question number 52, that very first one. So on 52, here's kind of the quintessential idea of when you use the electric field, when you use the charge, which charge are you talking about? So on 52, if I remember right, isn't like the electric field pointing to the right?
Yeah.
And then there's a 50 nanocoulomb charge. Is it 50? Isn't it?
Yeah, 5 nanocoulombs.
5 nanocoulombs? Okay? Now, here's the basic idea of how this is going to play out. So on the first one, you're going to figure out where you're going to put a proton. And again, you have to differentiate between, does it want to feel no electric field, or does it want to feel no electric force? Okay? And they're related, but they're certainly not the same thing. So if you look at the idea that you're going to put a proton somewhere, okay? So don't worry for now, just don't worry about the 5 nanocoulomb charge. If you put a positive charge out here to the right, what's it going to feel if that's the direction of the electric field? Is it going to be pushed to the right or pulled to the left?
Right.
It's going to be pushed to the right. So if you look at it in terms of that, so if you look at what's going to happen in terms of FEC, you have an electric field that's going to try and push that proton to the right. Now, here's the problem. If you put a proton over here, and that's also a positively charged particle, what's it going to feel from that positively charged particle?
It's gonna get pushed to the right.
It's also going to get pushed to the right. So if you put it to the right side of that 5 nanocoulomb charge, the electric field is going to try and push it to the right, and the repulsive force is going to try and push it to the right.
So it does you no favor.
So, which means there's no way it can add up to equal to 0. Okay? So off to the right is no bueno. Okay, it's not going to work. What if you put it over here on the left side? So if you put it over here, it's still going to feel a push to the right from the electric field, but if you put it over here, what's it going to feel from the 5 nanocoulomb charge?
A repulsive force.
That's going to
pushes
feel
to the
pushed
left.
back to the left. So that at least has the possibility of canceling things out. Okay? So then you run into, oh, okay, right? So I can set FEC equal to KQ1, Q2 over distance squared. Now, here's the main thing. If you look at this in terms of charge, okay? So is this charge here going to be the 5 nanocoulombs, or is that going to be the charge on the proton line? Because that's right, because you're talking about what the proton is going to experience. So is the electric field going to interact with the 5 nanocoulomb? Yeah, it is. Not the story. Okay? Because you need to focus on what's going to happen to that proton. So this is going to be the charge of the proton. Now, over here, this is going to be the charge on the proton, and then this is going to be the 5 nanocoulomb. So here's what's going to happen to the charge on the proton. What's it going to do? It's going to cancel out, okay? Because it's the same on both of them. So You know the value of the electric field. You know the value of that second charge. Make sure you put that into coulombs. And basically, you're going to solve for distance. Okay? Now, let's talk about an electron. So, your initial kind of gut response is to say, okay, well, if I'm going to have an electron, maybe the electron needs to go on the other side. Seems reasonable. If I put the proton on this side, maybe it would make sense that I put the electron on the other side, because it has a negatively charge.
No, that's not.
Okay? So, look at it this way. Just, again, don't worry about the 5 nanocoulomb charge. Just focus on an electron being in that field. You put an electron in that field, what's going to happen? Which way is, Alex, just let somebody else answer, please. If you put an electron in there, what's the electron going to feel? A push or a pull? Sydney. The electric field's going this way. I put an electron in the field over there. Don't worry about the 5 nanocoulomb charge, not part of the story.
Push?
Why?
Wouldn't it be a... Can you repeat the question one more time?
I
please?
can. I have an electric field going from left to right. Okay? I put a negatively charged electron over here. What's it going to feel? A push to the right or a pull to the left?
A pull to the left?
Why? You're right.
Because it's attracted to the... Well, because if the field's going this way, it means a positive test charge would push to the right. So the
Beautiful,
electron
because how do you
would
define the direction of an electric field? Based upon a positive test charge. Okay? So it's going to feel pulled to the left based upon the electric field. What's it going to feel relative to the positive 5 nanocoulombs? It's also going to feel a pull to the left. So if I put that over to the left, it's not going to work. The net effect of that is going to be a force to the left. But if I put the electron over there, it's going to feel a pull to the left because of the electric field, but then it's going to feel an attractive force to the right because it's being charged, attracted to that 5 nanocoulomb charge. So this is why your answers to 52 are the same. You would think that, oh, they should be on opposite sides because it's an electron and it's a proton. And no, you end up with the exact same answer. I promise you, tomorrow on the test, you have to understand that concept. And one of the things you have to focus on, are you focusing on that 5 nanocoulomb charge, or are you talking about the electron or proton that you're putting in there? So I promise you, in some form or another, that concept of 52 is going to be on the test. Make sure you understand that, okay? And why it's the same on both sides, regardless of charge, okay? So just point that out. 54 is a similar type thing. That ratio should involve a 4. So like 1/4 as much, 3/4 as much, something like that. Okay? 56, that's a good one. Read that as, I like that question a lot. You're better than average, likely to see a question like 56 on the test. So, here's the story. You got to find the volume using 4/3 pi r cubed, and then you got to find the mass of the bead. So, it's a carbon, atomic number, and I will give you this on the test. I'm not going to expect you to have the atomic numbers of all the elements memorized. So I would tell you, oh, hey, the atomic number of carbon is 6. So, out of that, when you get the charge on that, okay, and there's 6 protons and all that good stuff, your total charge is like 0.06 coulombs. Okay? Okay, something like that, around 0.06.
Wait, 0.06 or 0.006?
0.06.
Oh, I missed a zero. I see where I'm wrong. I had done it wrong the first time, and my final answer was 3.02 times 10 to the 19th newtons, which is a bit much.
Yeah, 0.06, 0.06.
Because I
Um,
that math.
Sean, I'm gonna need to see you.
And then the force should be then, when you calculate using KQ1, Q2 over D squared, that should be 10 to the 7th. Okay? And then, so I think that does it ask for like a fraction?
Yeah.
Okay? That fraction should be around like 1/30th, something like that. Okay? Now let's talk about 60. I like 60 a lot too. So here's what you've got on 60, mainly because of the fact that the capacitors are such a part of your daily life. Okay? Without capacitors, your phones really wouldn't work. Okay? So on 60, the first thing you have to understand is the electric field is Q over epsilon naught A. Okay? You got to start with that. The first thing you have to figure out is the value of the electric field, which should be a big number, like something times 10 to the 6th. Okay? Then, after that, you're going to find the force using the Jacob equation. Okay? So, you're going to take that. You're dealing with, is it an electron or a proton? Doesn't make any difference. So, this is going to be the charge on, which one is it? Electron? It's an electron, isn't it? No, it's a proton. This one's a proton. So, the force should be something times 10 to the negative 13th. Okay? On 60. So, your electric field is 10 to the 6th, but then you've got to roll that into calculating the force, because without the force you can't find the acceleration. So, the acceleration is something times 10 to the 14th. It's a really, really, really big acceleration, which can be pulled off over very, very short distances, because if you think about it, it's like, oh, we'll accelerate it for an entire second. Well, if you accelerated it that for an entire second, you're going 10 to the 14th meters per second, which is about a million times faster than the speed of light, because the speed of light is like 10 to the 8th meters per second. So this can be pulled off, but it has to be like an incredibly, incredibly, incredibly short amount of time. Because if you let this thing accelerate for a second, it's like, oh, great, we're going like a million times faster than the speed of light. So your overall answer on 60B, because then you have to roll that into that equation. So on 60B, that velocity should be something times 10 to the 5th meters per second. So when you get done, you got to find the value of the electric field, you have to find the force, you have to find the acceleration, and then you have to find the velocity. When it's all said and done, you should end up with something times 10 to the 5th. Is everybody cool with that process? Okay. Likely to see that as well. On 62, here's your triangle question. Yes, there's going to be a triangle question on the test. I promise you. I promise you. I promise you. In nanocoulombs, okay, in nanocoulombs, it should be, Gapshawn, this is for you. In nanocoulombs, it should be between 7 and 8. Is that a small enough gap?
I don't know, I didn't do it.
Hey,
Good
Mr.
enough.
Workamp.
I wasted a good gap.
No. We appreciated that. That was a really good gap.
Yeah, they got it for me. Good enough.
You, however, God, I wish I could go back and redo that letter.
2 letters.
Yeah. Those
Ice.
letters.
Dry.
Okay, on the spring problem, like the spring problem too. So your K value should be pretty close to 1, because if that's wrong, the whole problem is going to be wrong. Okay? So on the spring problem on part A, says what is the spring constant? Should be just a little under 1. Basically, all that is the slope of a force and elongation graph that starts at 0, 0. Okay, if you want to think of it that way. Okay, all you're doing is just finding the slope of that line. The magnitude of the charge, and this is what you have to be careful of. What do you use? So here's the basic idea on part B. Is that here's this spring, and you put the 2 charged beads on each side, and it's going to push this thing apart. So basically, here's the idea. The force to push the springs apart is going to equal to the electrostatic repulsion between the 2 particles. Okay? You set those 2 equal to each other, because that's what's making it expand. So, here's the story. How are you going to calculate, what 2 things do you need to calculate the force to make the spring stretch?
Spring constant and
K and
X.
X. And this needs to be K Q1 Q2 over D squared. Now, this is annoying, but welcome to physics. Are these 2 K values the same? No, they're both K, but they are vastly different. Okay? Vastly different. Don't look at that and go, oh, we can just cancel out the K's. No, bad. Okay? They are 2 completely different things. The units are completely different. What they represent are completely different. We're just stuck with having K's. Now, here's what you have to be careful of. Is this elongation here, is this X here going to be the same as that distance over there?
No.
Deacon, why did you say no?
The beads are attached to the end of the spring, which is 4 centimeters at the beginning, and after it's elongated, it's 8.5. But the elongation is only 4.5 centimeters.
Okay? So, this X here on that KX, does that represent the total length of the spring or how far it got stretched?
How far it got stretched?
This is your elongation. That's how far it got stretched. What does this distance represent?
Total distance of the spring.
The distance between the 2 beads. Okay? So, this is the distance between the beads. This is how far the spring gets stretched. So if all goes well on the spring problem on B, it should be between 30 and 35 nanocoulombs. So when you get done on B, it should be between 30 and 35 nanocoulombs. I don't hear a lot of, yes, that's what I got, responses. I not even asked you, Gapshawn. No. I haven't done. Thanks, Mr. Purdue. Okay, cool with that one.
Okay.
All right, let's talk about the sheet. bless you.
Oh, thank you. Oh.
Okay, so we're kind of gonna work through this, because I want to make sure that everybody has this one straight. So, what you want, if you look at this big picture, electrostatic force F on charge K is measured in the entirely negative x direction. So the only force this thing is gonna feel is going this way. And again, it's tough for me to overemphasize this, is you have to keep track. Is the question asking about fields, or is the question asking about forces, okay? They're related, but they're not the same thing, okay? Which one of those, the force of the field, you need two charges?
Force.
The force, because it's Q1 times Q2. If you're talking about an electric field, you only need what's creating the electric field. So this is going to be important. When you look at that equation for electric field, KQ over R squared, remember, this idea is analogous to the calculation of little g equals big G, mass of the earth over R squared. This is the mass of the earth or the moon. It's what's creating the gravitational acceleration. It isn't the dropper bottle that I'm going to let go of. It's what's creating the gravitational field. The same thing is true here. That Q is what's creating the electric field. It's not what's in the electric field, okay? What's creating it. There's a big difference between the two. Now, so let's just think this through. So, you know, this is a positive value. So, if that's the case, and this thing only ends up with a force to the left, okay, and it does. So what's the only way these vectors could end up with a force going to the left? And that's it. What would you have to have in terms of the forces acting on that point up there?
You have to have force y's that cancel out.
Yeah, you got to get rid of your y's, okay? Your y values have to cancel out. So the only thing you have left is your x values. So if you're a visual kind of person, you could have one force going this way and one force going this way. Seem reasonable? But it's exactly what Deacon said. These y values would have to cancel out, so you'd have to have the exact same y value, and then your x component is going to be going in this direction. So if this is positively charged, and you know that because you'd have to be given one of the values, okay? You'd know that would have to be a positive charge. So what would have to be the, I just want the sign. So what would have to be the sign of the 1.7 times 10 to the negative 6th value? Positive or negative? Positive. What about the other one? That would have to be negative, because that's the only way you could get that to happen. Okay, so that answer to A then, because of the fact that you're looking at this going, oh, okay, hey, if that's positively charged, Q1 is going to have a
Negative charge.
and Q2 is going to have a positive charge. Cool with that?
Nice.
Now, what if the force had been only pointing straight up?
The x's cancel.
Then the x's would cancel, okay? Then you'd have to have something like this, okay? All right. So on B, that's basically this diagram right there. You're going to draw the forces. Your answer to C, calculate the magnitude of the electrostatic force on part 3. Now, I'm going to show you the easy way to do this, and then I'm going to show you the very complicated way to do this, okay? So, which one do you want up first, the complicated or the easy?
complicated, so that way
Okay.
the easy feels refreshing.
All right, so the complicated version, because you know this is, what is it, 20, 37 and 53. And 53 degrees. Is that you find, and you know those distances. So the complicated version is that you know those two charges, and you use F equals K Q1 Q2 over distance squared, and you find the value of that vector. And then you use trig, because you know this angle is 53, so then you know if that's also going to be 53, you're going to know this angle in here is 37, because of alternate interior angles, all that good jazz. And then you can find the x and y components of that value. Then you would do the same thing with this, because you know that's 37 degrees, and then you come in here and you find those x and y components, and you do a bunch of trig, okay? And that's cool. So obviously, what's the only force you really have to worry about finding? What should happen to your y components?
Cancel out.
They should cancel out. Okay, that's an option. Now, here's the easier way, because it says calculate the magnitude of the force. So if you look at this, this is a 53-degree angle, and that's a 37-degree angle. Those together add up to what?
90 degrees.
90 degrees, which means this angle in here has to be a,
90 degrees.
okay?
Oh, this is the right triangle. So you can-
So it's a right triangle. So the short version is you just use the Pythagorean theorem. You still have to find the forces, but then you just use the Pythagorean theorem. Okay? That's the short version. Then you don't have to go through all of the hassle of finding the x and y components of it. Okay? So you'll get the same answer either way, but that just basically works out to be that hypotenuse is the resultant of those two forces because it makes a right triangle. So that's the short version. So your answer to C, no matter how you get there, should make an GPA times 10 to the negative third.
Nice.
Sounds about right.
Okay? Nice. Then you want the magnitude of the electric field at the position particle 3 due to the other two particles. So how are you going to get D?
A simple answer might be okay.
Beckett.
Goodbye.
Use the Jacob equation.
Jacob
Okay.
equation.
And because of the numeric values, that should also make the same GPA, but 10 to the third.
Well, everything checks out.
Okay. On E,
Check your direction.
you got boxes. Okay? So, on the figure, make an X where another positive charge can be fixed in place of the electrostatic particle on part 3 is 0. Now, what I'm about to show you, and Cohen, this is especially true for you,
Uh-oh.
I take no responsibility for what I'm about to show you,
Uh-oh.
okay? I wash my hands of this whole thing, okay? Where's my
Feel like 85. The circle.
Oh, and you screwed up 60. I didn't see the
What? 62.
Actually, no, I have a
Tough to say point two.
So,
Oh wait, what flavor is it?
Good question.
Oh boy, here we go.
No,
Yeah.
I don't. I
my
do not
hopes
have
up for
that.
no reason.
Sorry.
I probably have.
No, you're gonna get my hopes up until.
I was not working with spring problem, but yeah.
Adam,
You can
I
actually
have
have
a
a new one though if you want that.
You have
Yeah,
one?
like yours.
What's everyone I've talked about?
Yeah, no.
Well, no, this was like right
But then
my
some
word.
I have your
Electric
This
field
might be
hockey?
easier.
What is
Right
it?
there.
Ooh.
Yeah, but play that.
Your,
Lemon?
it's the area.
Or ginger.
Over E.
One of the two.
Wait,
It better not be ginger.
Equation isn't.
I think it's
Thanks.
not.
Sounds ginger.
I'm gonna sniff it first, as if I could smell it. I can't smell it.
Right.
oh, cause this is the capacitor again, and then it actually watches the electricity.
The one, that one equation is like
So
3 over
56 or
epsilon naught.
I'm like at 56, I got 60 right.
56, okay.
There's no
56?
Yeah, no,
that one is
Oh,
it doesn't smell.
After I erased it, really.
Taste it, tell me what it's
But hang on, I'm not copying.
been doing one
So
day.
find the volume, negative 5.24 times 10 to the negative 13
That's what it-
cubed.
Oh, okay.
Who does that? Get a cough drop and the first thing you do
I
is
did that.
BAM!
Okay, and you
I
multiply that by
mango.
2300 kilograms, and then times that by 1,000 grams to get
That's like
1.2.
terrifying. You're not afraid your teeth are just gonna like shatter or something? Like,
Wait, times 10 to the
sounds
negative.
like it,
That's flipping.
it sounds
Okay, let me actually try to figure out 56 before I.
based on the noise that came out of your mouth,
How many? You did.
on the shattering of that, I doubt that was.
That's where I was.
Okay.
Multiply by
To
1,000.
find the charge, right? Do you find
Or times it by 1,000.
the
No,
volume?
I feel it in my nose.
Depends on what you got.
That's probably
I
Typically,
went
the
the opposite
value
way.
of a
That
charge.
explains a lot, actually.
Are you sure?
Oh,
Oh, you
the
just messed
I don't know.
68,
I feel it in my nose.
56.
The outside of it was kind of like.
Okay,
And the
so
charge
this
based on
is
the
one
number.
listen to me. I am not responsible for what happens after I show you this, especially you, Cohen. So the goal is to get that positive charge in that goal, and you can use positive or negative charges, okay? So those are my options. So I can drag like a positive charge and put it, let's say, come on. Here. And then I hit start.
You should have put it closer so it went faster. Come on.
Go. You even get sound effects.
Wow.
Okay? Now, now you have a battery. Okay? So, you could, for example, drag a positive charge and put that here. And then you hit start. And it just goes in one direction because of Newton's first law of motion. So, what can I do to try and get it into that goal? Cohen, what's one thing I could do?
Make a wall of positive electrons below it so that it forces it back upwards. Like underneath the center charge.
So put electrons down here.
I mean protons. I meant protons.
So, a couple of them?
Yeah, a handful. Like 40.
Okay, no, I don't want to put it. Okay. So,
Further to the left. Or put more protons up to... You know what I mean. I can imagine what I wanted. That was not the left, that was the right, but...
over here?
Don't talk to me, no. Sit, be quiet.
Just use them.
It doesn't even let you bounce off anything?
No,
That's cruel.
sorry.
So
what can I do?
Make a scoop.
Get an electron next to the wall
Hi.
and have the.
Make a big hook shape.
Put an electron close to the wall like here,
Yeah, that sounds
But
about right.
like, with a,
okay?
And try and get it to swing around, but then again, this ain't orbits.
Remove those protons.
Make a big L shape with protons.
No, you make a racetrack.
you kind of surround it on both sides. You know, like the tires like on a racetrack.
Oh, yeah.
So,
And if you do it like...
put a proton here,
Make it in there.
Electron
No,
at
start
the end.
electron on
narrow
the
and make it
end.
wider, it'll just constantly
In sense of going
accelerate.
Yep. We can do orbital.
Can you
So
do
if this
that?
has got it around, Kill, you, Miss Soccer Player, now what?
Electron flying the globe.
Put a bunch of electrons in the bowl, and that works. I was gonna say if you put like another proton on top.
Put an electron back there, maybe another electron back there.
Because if you put a proton,
How do you put a proton up there as well to stop the flow?
yes.
Yes.
Yeah, and put a proton like,
Because you need
Yeah.
a proton there to push it back. That
So put a proton where?
about 1/3 the way away from the wall, a little above the goal.
There?
Yeah.
to the right.
Alright, cool. How about a couple protons? Why not? 30 electrons. Just scatter them about.
Okay. Now, that's level 1.
Level 3.
Level 2 is this.
Oh.
What's the last level?
Level 3 is this.
Yeah, right.
Now,
Yeah, right.
we don't have time, but I'll show you a video of one time I had, that was when I didn't have snow days. So I'm gonna show you a video of what one class was able to do. So, I gotta disconnect this and switch over to this computer.
Mr. Rice.
You said it's called electric field hockey? I'm doing
Yeah.
physics focus
And
this way.
electric, this is,
I know,
I said,
I'm
I am not
I'm
responsible.
gonna do that all day in class.
Or we do
all
like
day.
the fuse by the proton as possible.
I'm a master at breaking physics engines. Give me
Yeah.
like 30 minutes.
Yeah, they're not hard to
Mouse.
break.
No,
5.
you just put like a proton and electron in the same spot.
5 minutes.
No. It'll just do nothing. It'll treat like it's not there. What you really want to do is you put like 40
No, it was-
protons and then a bunch of electrons and you make just a cannon.
Okay,
Or a bunch of protons in a V shape.
Yes.
She just
I bet you can get it going fast enough that it just clips through that collision wall. It would
All right.
mag out your
So-
cells.
back to recording.
Do I look like I care?
So this is level 2, and
Are you offering extra credit for those of us who can?
no, but, and so literally what I did is I went around the room and said, hey, you do this, you pick the next one, and we just went around. Now, so this is what we settled on. So, we've got like a whole bunch of like negatively charges and positively charges. So you have to watch the path of the ball. Completely off the screen. It was the wildest. It probably took us like 10, 15 minutes to pull that off. That is the wildest one I've ever screened where it goes completely off the screen and then magically comes back. So,
Fine.
uh,
Let's see if I can draw a picture with one.
I'll play it again.
Yep, started. Good?
Yeah.
Okay. Yep.
Whoop. Whoop.
Left like the orbit.
It's back. I'm sure it does look like Matthew Barnard.
Yep, started.
So that's why I said I am not responsible for how much time you potentially spend on this game. So I'm just saying.
I have an idea for one.
Yes.
Yeah.
Just you wait, nerd. I'm gonna create the sun.
But yeah, that was the wildest one, the one that it did that all the way around. On the question on the back. So, at which position will the electric field due to these two charges be 0? How many have an angle work upwards from the bottom? How many have E?
Wait. For
On the back side?
Oh, did we ever finish what E actually was on the?
Oh, E, okay, speaking of which, yeah, let's finish that up. So,
There's no signal on your laptop or iPad.
Danny, you're so picky.
Well, the camera can't see it.
I don't care.
Oh, okay.
Okay, so,
Group of people are here.
so
Hey,
what does
I'm taking the
everybody
sacrifice
have
for
as your
you.
answer for E?
Top left.
Yeah, top left.
This one?
We still can't see it.
I'm still taking the sacrifice for you. Just a little propaganda. No propaganda.
There we go.
There we go.
Yeah, I don't know.
So define top left.
The middle. That one.
This one?
Yeah.
Yup.
That is accurate.
Very good.
Yes.
Everybody cool with that answer?
Yes.
You should be.
Nice.
Go!
Next.
Okay. Now, when it says justify your answer, what did you write out of curiosity?
Hang on.
The position will allow the positively charged particle to only apply an opposing force since particle 3 has a positive charge.
So yeah, so basically the short version is it's gonna repel and you're gonna make everything cancel out. So that's the short version.
Oh, it is.
Okay, the question on the back. How many have E as an answer? D, C, B, A. The A's have it? That's the right answer.
Oh no, I just realized.
So on that backside, A is the correct answer.
And minus 1.
I just realized. Oh yeah.
I just kind of thought through it with
Yes,
this,
the
but
correct
then
answer.
I did it
Good.
correctly. Yes, you know the
Second.
total is 0.
Not the right answer.
This
I'm
one.
getting what you get at.
This should have not worked.
A, I got 0.985 feet.
Yes.
Yeah,
Oh,
you
no,
know,
like,
like
he
he
doesn't
doesn't
like that.
And then B, I'm doing something that's like gonna be 10 centimeters.
Bless you.
Where's the using
Wrong.
He did like 6
Wait, sorry, you got like a slightest sniffle. I'm seeing like take up so much.
Oh, wait.
I want you to know, I've only sneezed like, what, 40 times. Highest scoop is 3.
Yeah.
For
No,
third
no,
one,
I
though.
multiply by 10 instead of dividing by 10. I get 33 there.
Okay, that's what you would. You would seem like
Yeah,
10 plus
very much
times
the
a
best.
day.
2 equals 1.
Yeah.
No, wait.
This one? I was getting the same.
3.32 times 10.
Excuse me.
This one also, or like my
Equals
actual.
33.
Oh my god.
Oh my god.
I got it.
That's your favorite.
This one? For C and D? No. 5 C
Just to the edge.
Just to 5 meters. My D never fails. That's what it is.
I don't
I haven't done the string problem yet. I'm doing the string problem.
The ugly
That's
one.
literally
The ugly one.
That's probably gonna be it.
I didn't know.
Oh, like, just go 5 and 4. Go 5 and 4.
Here?
It's like this feels right.
Maybe do that.
Oh, I forgot. Whoops.
If you put in something all
Okay, so I'm gonna shoot a proton between 2 plates of a capacitor.
I've sneezed.
Don't do it.
Okay, it's gonna be moving at 5.6 times 10 to the 7th meters per second.
That's the distance.
The electric field has a value of 14,000 newtons per coulomb. The plates have a length of 5 centimeters. I want to know how much and in what direction is the proton going to be deflected. So, let's start with this idea. What's the direction of the electric field inside the plate capacitor? Does the electric field point up or does the electric field point down?
Down.
Why, Will?
Positive, negative.
Yeah, so if I put a positively charged proton, I know the direction of my electric field is gonna be pointing downward. So when that proton comes in, you know that the proton is gonna take some path down like this. Cool. Okay. So if I know the value of the electric field, what could I find?
Force.
Of course.
Could find the force, right? Using the Jacob equation, I could use effect. So I've got an electric field of 14,000, which is pretty strong. Newtons per coulomb. What am I going to use for Q?
Charge on the
proton.
Charge on proton, which is what?
1.6 times 10 to the negative 19th.
1.6 times 10 to the negative 19th coulombs. My coulombs cancel out, I get newtons. So somebody take I just made up these numbers. So somebody take 14,000 times 1.6 times 10 to the negative 19th. Sometimes,
2.24 times 10 to the negative 15.
what'd you get?
2.24 times 10 to the negative 15.
Okay,
24.
2 point what?
24.
My bad. Bless you, bless you. Okay? Now what can I do?
Find an acceleration.
Why?
Because we know the mass of a proton.
So, you know that F equals ma. Now, here's my question. You all have done problems like this before, way back when life was simple, when you were in physics 1. What is this actually modeling? It's a lemming problem. It's a lemming problem. What happens in the X,
Stays in the X.
what happens in the Y,
Should stay the Y.
stays in the Y. So will there be any horizontal acceleration?
No.
What's the only direction you're going to have any acceleration?
Vertical.
Verticals. That's like me throwing a golf ball off of a cliff. This is just a lemming problem applied to a parallel plate.